Hello. This video is for anyone who wants to learn Python using math or learn math using Python. It is also for anyone who wants to see how many math problems can be more easily solved by writing a Python program. Today, we will learn how to solve practically any geometry problem with the help of a computer using only an internet browser. We will introduce concepts such as computational geometry and interactive geometry systems. Python library Shapely will serve us as an introduction to computational geometry. And Colab IPy widgets together with Matplotlib will serve as a guide to interactive geometry systems. Interactive geometry systems like GeoGebra or CAR are valuable tools for learning geometry. You can observe the capabilities of the GeoGebra system right in front of you. These programs are designed to create and manipulate various geometric figures. GeoGebra showcases its users the ability to craft and modify geometric shapes, like triangles and circles, adjusting their size and relative positioning. Upon sketching these desired figures, mathematical computations related to them can also be conducted. An exemplar of such interactive geometry systems, GeoGebra, is tailored for educational purposes, catering to learners from elementary to university levels in mathematics and science. Frequently, these interactive geometry systems offer two modes, a 2D and a 3D environment. While initially you witnessed the capabilities of the GeoGebra system within a 2D setting, you are now introduced to the fundamental components of this system in a 3D context. GeoGebra served as my inspiration to endeavor into creating something akin using Python and Google Colab. To illustrate the versatile applications of Python and Colab in geometry, let's consider a problem extracted from a final school exam. The problem statement involves an obtuse triangle ABC. Notably, the disparity between angles A and B amounts to 90 degrees. Additionally, the ratio between the lengths of sides AC and BC equates to 3/4. The task at hand requires the computation of the tangent of angle A. In order to adhere to conventional problem-solving methods, akin to those favored by examiners, we will first employ Python as a proficient calculator before transitioning to an interactive geometry solution. Hence, the resolution takes form on a physical sheet of paper, accompanied by a pencil. To streamline notation, we shall represent the angle as alpha. Subsequently, the selection of either the sine or cosine theorem becomes pivotal. Had we been provided with two sides and the angle between them, the cosine theorem would have been the optimal choice. Nonetheless, in the current scenario, information is furnished concerning two sides and their adjacent angles. Consequently, opting for the sine theorem emerges as the more suitable approach. For the sake of simplicity, we will designate the side lengths as 4 and 3, despite being provided with the aspect ratio. This simplification, importantly, has no bearing on the angle-related outcome. Moving forward, we grasp the angle subtraction formula, utilizing the expression sine alpha minus 90, which subsequently yields minus cosine alpha. To conclude, recalling that the tangent corresponds to the ratio of sine over cosine, the resultant answer materializes as minus 4/3. Expanding on this solution, the utilization of Python's SymPy as an efficient computational tool can be introduced. Let's take a brief look at this alternative approach. Initially, we define two symbolic variables, x and y. Subsequently, two equations are established. The first equation straightforwardly equates y to the tangent of x. The second equation succinctly presents the theorem of sines. It becomes evident that x directly represents angle A within our triangle. The solve method offered by SymPy then effectively solves the equation system. The solution is then promptly printed for reference. Now, let's transition to our central subject. exploring interactive geometric systems and computational geometry, utilizing Python and Google Colab. To proceed, let's access the Colab document through the link provided below this video. Prior to delving into the specifics of the code and techniques, let's first observe the final outcome. Before us lies a depicted triangle that partially aligns with the stipulated problem's conditions, featuring sides measuring 3 and 4 units. An automatically generated green boundary consistently connects the blue and red borders. Located at the drawing's apex, a modifiable parameter called the rotation angle becomes apparent. Upon elevating the rotation angle parameter, a corresponding adjustment causes the blue and red edges to rotate, effectively morphing the triangle to match the problem's specified conditions. Adjacent to the drawing's right side, a simulated whiteboard serves as a platform to exhibit calculation outcomes. Sequentially, by iteratively increasing the rotation angle, we approach the triangle configuration as stipulated in the problem. This adjustment ensures the fulfillment of the prerequisite that the disparity between angles A and B amounts to 90 degrees. Evidently, through interactive manipulation of the triangle's orientation, the accurate solution unfolds. Now I'll elucidate the central elements of the primary code used in this demonstration. An important aspect to address is the organization of code libraries within a Colab document. To accomplish this, we'll navigate to the dedicated Colab section, Classes and Functions. Within this segment, we encounter the concealed code that necessitates execution to load the classes and methods for subsequent use. Let's proceed with running this code. Should you wish to inspect the code itself, you can do so by clicking on the Show Code link. Upon accessing the hidden code, the declaration of the Python class triangle becomes visible. This class encompasses all the essential methods required for triangle-related calculations. As this code is sufficiently extensive and can be employed across various sections of the Colab document, we've chosen to conceal it to maintain a more streamlined appearance. The subsequent stride in comprehending the interactive resolution to our problem involves the implementation of the interactive interface. The following code snippet directly addresses this objective. We make use of the IPyWidgets library. Commencing with the design of the numerical bar element, we subsequently invoke the interactive method from the widgets module. Within this method, we provide the numerical bar object and reference to the function f. The function f in this context assumes the role of both illustrating the image and conducting other desired calculations. On each alteration of the numerical bar parameter, this function will be invoked. Subsequently, we establish a function to generate the coordinate system illustration, an essential component of the Cartesian coordinate plane. I won't delve into an exhaustive commentary on this function, but it's worth mentioning that it relies on standard features of the widely recognized Python library, matplotlib. Naturally, we ensure the integration of this function within f, which inherently gets invoked each time the rotation angle is adjusted via the interactive numerical bar element. Our initial exposure to the domain of computational geometry within the Python library, Shapely, is next in line. This library facilitates the automation of diverse computational geometry calculations. Our introduction commences with the utilization of line-string. For our specific problem, this will merely represent a segment linking 2 points on the coordinate plane. Within the confines of the f function, we outline 2 segments. These segments will correspond to the sides of our triangle, subject to rotation to achieve the desired transformation of the triangle. Following this, we proceed to visually render these two segments within the coordinate system. Additionally, we depict the third side of the triangle, highlighting it in green. Let's explore the shapely methods that are integral to transforming a triangle. As evident, we utilize the rotate and translate methods of the geometric entity to accomplish this. We establish the central point around which the rotation will be executed. Subsequently, we effortlessly apply the rotate method to our segment, specifying the rotation angle parameter x and the rotation center. The outcome is the display of the rotated segment within the coordinate system. This identical approach is undertaken for the second side of the triangle. In this case, a noteworthy addition precedes the rotation. Prior to rotating, we compute the required shift for the second edge, ensuring its endpoint aligns with the endpoint of the initially rotated edge. Achieving this involves leveraging Shapley's translate method for displacement. Subsequent to the displacement, we proceed to rotate the second side by the appropriate angle, subsequently rendering it within the coordinate plane. Finally, we conclude the depiction of the transformed triangle by graphing the third side. Furthermore, we take the initiative to label the angles of the triangle as A, B, and C. In this manner, it becomes evident that with the appropriate Python libraries at our disposal, we have the capability to construct an instance of interactive geometry within a web browser. I trust you found value in this video, acquiring not only mathematical insights, but also a range of novel technical approaches.